Out there, past the light of familiar stars, are places where the rules stop working. Drop a planet, a star, even a beam of light into a black hole, and it's gone. No signal, no echo, nothing. Or so we thought. For more than a century, scientists have chased a question as vast as the darkness itself. When the universe's hungriest objects swallow matter, energy, and information, what becomes of it all? Does it vanish forever, breaking the laws of physics? Or is some hidden record kept beyond our reach? From Einstein's first equations to modern telescopes stitching the Earth into one giant eye, each discovery has peeled back another layer of mystery. Join us as we travel from the death of stars to the edge of the unknown, exploring what black holes reveal and what they still refuse to give back. In the long winter of 1916, while Europe groaned under the weight of war, a quiet but world-changing idea slipped across a desk and into history. Albert Einstein, exhausted from years of wrestling with gravity, had only just finished laying out the field equations of general relativity, an attempt to describe how matter and energy bend space and time themselves. These equations were strange and difficult, filled with curved geometry and an almost dreamlike sense that the universe was a flexible thing, not the rigid stage people had assumed for centuries. Most scientists were still catching their breath, still trying to understand what it meant for starlight to bend as it passed the sun, when another man took those equations and walked further into the dark than anyone expected. That man was Carl Schwarzschild, an accomplished physicist who had volunteered for the German army, despite being in his 40s and already in poor health. From the mud and cold of the Eastern Front, where shelves shook the earth and men disappeared into trenches, he managed to find moments of quiet to think. In December of that year, as the world fought and froze, he sent Einstein a letter. Inside was a solution to the field equations, crisp and exact, something Einstein himself had not found. Schwarzschild's work described the space around a perfectly spherical mass, but with it came an unsettling implication. If enough matter was crushed tightly enough, the pull of gravity would grow without limit, until light itself could not escape. Einstein read the paper and was impressed, but even he seemed reluctant to believe what the math said. The word singularity was not yet used in the way we know today, but the seed of that idea was there. A place where the known laws break down, where density and curvature shoot to infinity. For most physicists, the notion felt too extreme to take seriously. Space swallowing light? A star collapsing into an invisible pit? It sounded closer to myth than to science. Still, long before Schwarzschild, there had been whispers of something similar. As far back as the late 18th century, bodies so massive their escape velocity would exceed the speed of light. Mitchell wrote about them in 1783, when no one even knew light speed exactly, imagining whole worlds hidden from view because nothing, not even a beam of light, could get free. But these ideas had faded as Newton's simpler picture of gravity held sway, and because there was no evidence such objects existed. Now, with Einstein's new picture of a pliable universe and Schwarzschild's solution in hand, the idea returned, more precise, more haunting. Yet in 1916, the world had no appetite for cosmic monsters. Observatories focused on practical matters, mapping stars, studying planets, following comets. The sky was a known place, elegant and predictable. No one had seen anything that behaved like a black hole. There were no X-ray telescopes, no radio arrays, no way to sense something that gave off no light. Even Einstein himself thought nature would conspire to keep such extreme objects from forming. He assumed real stars might explode or shed mass before reaching the critical threshold that his own theory allowed. The Great War took Schwarzschild before he could explore further. His health worsened in the trenches. He died in May 1916, at just 42, leaving behind equations more enduring than any fortress. His name stayed attached to that invisible surface where escape is impossible, the Schwarzschild. Radius, but for decades, it was an elegant curiosity. Not a doorway anyone believed real stars could cross. As the 1920s and 1930s unfolded, astronomy advanced but slowly. Telescopes grew, spectra of starlight were charted with new care, and distant galaxies were recognized thanks to Edwin Hubble's work. Yet the specific threat hiding in Schwarzschild's math stayed quiet. Scientists who stumbled across it treated it as an odd corner case, something tidy but unphysical. A black hole, though the term was not yet coined, felt like a clever joke, not a prediction. And yet, outside the professional world, there was a strange poetry in the idea. Writers and dreamers spoke of collapsed suns and dark abysses. Philosophers asked what it would mean for a place to exist from which no signal could return. The universe seemed to contain more mystery than the textbooks suggested. And some younger scientists began to wonder if the impossible might one day be seen. In this way, the first shadow entered. Human thought, not as a picture or a confirmed object, but as a quiet, unsettling note in the symphony of physics. A soldier scientist scribbled from the front and unknowingly opened a path to the greatest voids we know. Light bent, time slowed, and deep in the math, the idea of a one-way surface took root. Nobody had yet seen a black hole. Nobody could prove one existed. But the dark possibility was there, a seed waiting for instruments and daring minds to find it. While the rest of the world carried on believing space was safe and stars would always shine. A star is not born to last forever. It begins in a cold cloud of gas and dust, where hydrogen atoms drift quietly for millions of years until a ripple of gravity pulls them closer, heating them until the first sparks of fusion light appear. For a long time, the star seems eternal, shining with steady strength, but deep inside, at its core, a slow clock starts the moment that fusion begins. Hydrogen, the simplest element, is pressed and fused into helium, releasing enormous energy that pushes outward against the weight of the star's own mass. This balance outward pressure from burning fuel against the relentless inward pull of gravity is what keeps a star round, bright and alive. But hydrogen is not endless, and once it thins out, the balance begins to tilt. In stars like our sun, the end is gentle, but in the giants, those many times heavier. The final act is far more violent. When hydrogen at the core is spent, the star does not die quietly. It contracts and heats, igniting new shells of fusion, helium into carbon, carbon into heavier elements like oxygen, neon, and silicon. Each stage is shorter than the last, like a heart beating faster as death approaches. A star the size of Betelgeuse, for example, can burn hydrogen for millions of years, helium for hundreds of thousands, carbon for just centuries, and iron the last step for mere hours. Iron is a trap, for when fusion reaches it, no more energy can be gained. It costs more to fuse iron than it gives back. The core becomes a silent, growing weight at the center of unimaginable heat and pressure. When enough iron builds up, gravity finally wins. The outward pressure that has held the star against collapse falters in an instant. In less than a second, the core implodes, matter falling inward at a quarter of the speed of light. Temperatures soar to billions of degrees, atomic nuclei shatter, protons and electrons are crushed into neutrons. The core, once hundreds of thousands of kilometers across, shrinks to the size of a small city. Above it, the outer layers of the star, suddenly unsupported, crash inward too, and then rebound, meeting a shockwave of released energy so powerful it outshines whole galaxies for days or weeks. This is the supernova, one of the most luminous events the universe knows. To stand anywhere near it would be death, long before the light reached you. Even across vast space, the radiation could sterilize worlds. For a few heartbeats of cosmic time, the dying star is a beacon so fierce it can be seen across millions of light years. It is also a forge, scattering gold, uranium, and the other heavy elements that make planets and bones and rings. Every piece of iron in your blood was cooked in such a death. Sometimes. What remains after the blast is a neutron star, dense but still tangible. Yet if the original star was massive enough, perhaps 20 times the mass of the sun or more, even that remnant cannot resist its own weight. Gravity drags it further down, crushing every atom, every quark, until the known physics stops being enough. The collapse continues past anything we can picture. The surface disappears, and light cannot climb out. What is left has no familiar shape or substance. To the outside world, it is only a region of space with gravity so intense that beyond a certain invisible boundary, the event horizon, nothing can return. For a long time, this idea that the death of a giant star could create a place where all paths lead inward and no message escapes was more nightmare than accepted fact. Physicists could write the equations, yes, and the math was clear that once enough mass collapsed into a small enough radius, escape became impossible. But there was a deep discomfort in describing a thing you could never touch, never see directly, and perhaps never understand. Einstein himself doubted such perfect collapses could happen. Many astronomers believed stars would blow themselves apart before reaching this extreme. Still, the universe is patient and offers evidence in its own time. As telescopes grew stronger and detectors reached beyond visible light into X-rays and radio waves, faint clues appeared. There were stars dancing in orbits that made no sense, tugged by invisible partners. There were regions bright with high-energy radiation, yet empty to ordinary sight. Slowly, a new picture began to form. The violent death of massive stars really could end in something darker than night. Trying to picture what happens inside pushed human imagination to its edge. Some thought of matter squeezed infinitely. Some imagined space curving back on itself. Some dreamed of tunnels to other realms. But beyond the poetry was a cold fact. Whatever fell past the horizon would not return in any form we know. Light, time, information, all lost to the outside world. And yet, paradoxically, the very act of swallowing seemed to shape the universe beyond, influencing nearby stars. Bending the paths of whole galaxies, a star's last breath is not just an ending, but a threshold. The supernova makes gold and memory. The collapse that follows creates a black hole, a one-way door deeper than language. What began as simple hydrogen shining softly becomes something that challenges physics itself. And from the moment the first of these silent monsters formed, long before Earth existed, the universe held pockets of mystery that would one day catch human eyes and questions. The death of a star, in its violent and beautiful collapse, is where the road to black holes truly begins. A road lit by explosions and ended by silence. In the decade after the Second World War, astronomy began to change from the quiet art of watching visible starlight into something far stranger and more powerful. Radio antennas sprouted in farm fields and on lonely hilltops, enormous wireframes and dishes aimed at the sky like listening ears. The Cold War pushed technology forward. Radar engineers and physicists built instruments able to detect whispers from space that the human eye could never see. Among those who came of age in this moment was a young graduate student named Jocelyn Bell, working at the University of Cambridge in the mid-1960s, stringing miles of cable across a field to create a radio telescope sensitive to the rapid flicker of distant signals. The work was muddy and often cold, the air damp with English rain. But Bell was meticulous and patient, sorting through endless rolls of chart paper for patterns. Most people would miss in July 1967, she noticed something odd, tiny, perfectly regular pulses on her charts, coming every 1.337 seconds from a point in the sky. These blips did not behave like any known star or planet. At first, in private notes, she and her supervisor Anthony Hewish joked nervously about LGM little green men because the signals seemed almost artificial. But as they searched further, they found more of these pulsing sources. Each rapid and stable, too strange for ordinary stars, but too natural to be alien transmitters. They were soon recognized as pulsars, the radio beacons of neutron stars, the dense, spinning corpses left after supernova. Bell's discovery was a turning point. It proved that extreme remnants predicted by theory were not just mathematical curiosities. They existed, and we could find them if we built the right tools. Once the door opened to this invisible universe, others followed. Astronomers realized the cosmos was filled with compact, dark things that ordinary telescopes could not see. Radio and optical methods were joined by a new generation of X-ray detectors, lofted above the atmosphere on sounding rockets, and later, satellites like Uhuru launched in 1970, Earth's air blocks most X-rays, So until these instruments flew, no one knew the sky blazed with hidden sources. Suddenly, space looked alive, with invisible valence binary systems, where a dense object fed on a companion star. Disks of superheated gas shining in wavelengths no human eye could perceive. Among the most riveting of these new lights was Cygnus X1, found in the constellation of the Swan. By the early 1970s, data from Uharu and other satellites showed an intense X-ray source locked in orbit with a massive blue star, HDE 226,868. The blue star was visible through ordinary telescopes, but its unseen partner gave off only X-rays and pulled with ferocious gravity. Careful measurement of the star's wobble suggested the hidden object weighed far more than a neutron star could. Its mass was at least 6, perhaps more than 10 times that of our Sun. The math said that at such weight, unknown material could hold itself up. Nothing but a black hole fit the observations. The reaction among scientists mixed awe and unease. For decades, black holes had lived safely in the realm of theoretical physics, places the equations allowed, but no one expected to meet. Now here was a candidate roaring in X-rays, just 6,000 light-years away. The term black hole, coined a few years earlier by John Wheeler, caught on fast because it captured both the stark physics and the human feeling, a hole in space from which nothing returns. Even skeptics had to reckon with Cygnus X1. Its gravity and emissions matched the predictions too neatly to dismiss. What made the moment electric was how suddenly the impossible turned real. Einstein himself had doubted such perfect collapses could form, and yet the observations matched his own general relativity. Astronomers who had spent their careers mapping quiet stars were confronted with objects that defied ordinary thought, collapsing past sight and feeding on their neighbors. Some found it thrilling, the universe larger and wilder than textbooks promised. Others felt a shiver, as though nature had kept secrets far deeper than anyone wanted to believe. In the same years, cultural echoes of this new darkness spread. Popular magazines featured artists' impressions of space warped into funnels of light bending in graceful arcs. Science fiction leaped on the idea. Films and novels spoke of voyages to the edge of the event horizon, of time slowing and escape lost. But behind the images was serious, careful work. Binary orbits measured night after night. X-ray counts tallied from fragile detectors in space, spectrographs reading velocities with painstaking precision. It was not easy glamour, but hard, cold confirmation that the math was right. The discoveries built a bridge between theory and sky. Jocelyn Bell's pulsars had shown neutron stars existed. Cygnus X1 suggested some collapses went even further into the full darkness of a black hole. As the 1970s closed, no one could pretend black holes were just playful speculation. They were out there, invisible but hungry, and human tools were now sharp enough to sense their pull. This shift changed more than astronomy. It altered how we think of death and permanence in the cosmos. Stars were no longer eternal beacons. Some could die so completely they left behind only gravity itself. Space was not a safe, empty backdrop, but a landscape with hidden predators. And for scientists, perhaps the most haunting change was realizing that their own equations had foretold this long before they believed it. The impossible was never impossible. It was waiting, silent, till technology caught up and eyes opened. When astronomers first began to talk seriously about black holes, the words themselves could not keep up with the strangeness of what the equations demanded. At the heart of every description sat one defining feature, something both simple and terrifying, a boundary. Later it would be called the event horizon, but before the name settled, scientists spoke of the Schwarzschild radius, the critical distance from the center where escape becomes impossible. Unlike a wall or a surface you might imagine touching, this boundary has no physical substance. It is simply the place where the mathematics says all paths, even those followed by light itself, bend inward forever. Cross that invisible limit, and no signal, no photograph, no pulse of any kind can make its way back. To grasp what that means, it helps to think about how general relativity rewrote gravity. Newton had pictured an invisible force pulling objects toward one another. Einstein showed that mass and energy actually bend the fabric of space and time. Light, which we think of as the fastest and most unyielding traveler, simply follows the straightest possible path through that curved geometry. Near a massive body, the straight path bends inward. The heavier and more compact the body, the deeper the well. For ordinary stars, the well is shallow enough that light can still climb out. For a black hole, the well steepens so drastically that all possible routes turn back toward the center. Time itself does not behave normally close to this edge. According to the equations, a clock falling toward a black hole ticks more slowly as it approaches the event horizon when compared with a clock far away. To an outside observer, watching through a telescope, the falling clock appears to freeze and fade, its light stretched into redder and redder wavelengths until it vanishes. The traveler carrying that clock, however, would not notice anything special at the boundary. They would drift across without a jolt. Yet from the outside, it looks as though time has stopped just shy of the horizon, the final moments suspended forever. This odd split in perspective, one story for the infaller, another for the distant observer, unsettled early thinkers, and still fascinates anyone who studies relativity. Light, too, is distorted almost beyond recognition. Photons climbing out of the deep gravity well lose energy. Their color reddens until it disappears. Space itself seems to stretch, distances warping in ways Euclid never imagined. The region outside the horizon is not normal either. It is bent and twisted so severely that orbits become unstable and radiation fierce. Matter spiraling inward forms an accretion disk that glows hotter than most stars, but if any part of it crosses the horizon, that light will never return. For a long time, scientists assumed this horizon was absolute, a perfect one-way gate. Whatever fell inside was lost, not just in practice but in principle. The very information about what had crossed seemed to vanish from the universe. Drop a library, a mountain, or a planet. From the outside, the black hole would keep only a record of total mass, electric charge, and spin. No trace of the details would remain. This view felt safe mathematically, but deeply troubling. Physics had always assumed that information, at least in theory, was conserved. You could scramble it, but not erase it completely. Here was a place where the rules seemed to break. It was partly this feature, the vanishing of information, that made black holes seem like monsters in the early imagination. They were not just heavy objects. They were places where the universe forgot. Even Einstein tried to believe that nature would avoid making such perfect traps, perhaps through some counterforce or instability. But as observations of Cygnus X1 and other candidates built up in the 1970s, and as the mathematics of gravitational collapse became harder to dismiss, the horizon grew from a curiosity into a physical boundary that the cosmos itself seemed willing to draw. Scientists tried to picture the experience. Suppose an astronaut fell toward a stellar-mass black hole. From the ship's own perspective, there would be no sudden wall, no flash of light. The crossing would feel uneventful. Yet tidal forces would grow, pulling on feet and head with different strength, stretching the body into a long thread in a process nicknamed spaghettification. To someone watching safely from afar, the astronaut would never be seen to cross. Instead, they would appear to slow, dim, and finally fade at the brink, their last signals arriving ever more redshifted and weak. This strange dual story, smooth for the infaller, frozen for the observer, revealed how relative time and distance become near the horizon. The idea that nothing could return also pushed theorists to their limits. Could particles somehow escape? Could quantum effects allow a leak? In the 1970s, Stephen Hawking proposed that the horizon was not entirely black, that quantum fluctuations could let tiny amounts of radiation seep away, eventually causing the black hole itself to evaporate over vast times. But at the time of the first modern studies, before Hawking's insight took hold, the horizon seemed final and silent. It was a cosmic silence so complete it felt almost unnatural. For the public, and for many scientists, the image of this trap caught the imagination more than any other detail of relativity. Here was a place where time could slow to nothing, where light could not find a way out, where the normal bookkeeping of the universe might fail. And yet the horizon had no physical edge to touch. It was a mathematical shadow that once crossed, shut a thing off from every future we could see. In understanding this, astronomers began to accept that black holes were not just exotic predictions, but real features of nature. The event horizon was not metaphor, but geometry itself, and the universe, it turned out, was willing to build such perfect doors and keep their secrets. In the summer of 1977, two small spacecraft left Earth on silent arcs that would carry them farther than any machine had ever traveled. They were called Voyager 1 and Voyager 2, identical in most ways. Built by engineers at NASA's Jet Propulsion Laboratory in Pasadena, their aluminum frames crowded with instruments, cameras, detectors, and a long, thin boom carrying a dish to whisper data home. At first, their purpose was practical and ambitious, but still bounded. They were meant to tour the giant planets, to fly past Jupiter and Saturn, taking close photographs and sampling magnetic fields, maybe pushing on toward Uranus and Neptune if the craft lasted that long. Yet almost from the beginning, there was another layer to the mission. Something quieter and stranger, a decision to send not just machines but messages. On each Voyager, the engineers bolted a golden phonograph record, carefully protected in a cover of aluminum, etched with simple diagrams. One image shows a man and a woman, another shows a map of pulsars to triangulate our place in the galaxy. Arrows and symbols describe how to play the record and how long the pulses of hydrogen take, an attempt to talk across unimaginable gulfs to anyone, or anything that might find it. Inside are sounds and music. Greetings in 55 languages, a baby's first cry, a kiss, Beethoven and Bach, Peruvian panpipes. Chuck Berry's Johnny Be Good, the brainwaves of a young woman named Ann Druyan thinking about falling in love. Carl Sagan and a small team chose these things in the summer of 1977. A hurried committee for the voice of Earth. They worked in rooms where sunlight came through, dusty Pasadena windows, and argued about which songs to send, which photographs to pack. Knowing the odds of anyone ever hearing were nearly zero, but feeling it mattered anyway. This gesture, to cast our story outward into the deep dark, said something about the kind of creatures we are. At the same time that physicists were describing black holes as perfect traps, swallowing light and time and perhaps even memory, humans were scratching messages into metal, hoping the universe itself might one day read them. It was almost defiance. If some regions of space erase, then somewhere else we will insist on leaving a trace. By the time the Voyagers launched, the idea of black holes was no longer fringe. Cygnus X1 was well known. Quasars were understood as supermassive black holes feeding on distant galaxies. And theoretical physics had grown comfortable with the concept of an event horizon. Scientists knew that, scattered across the sky, there were invisible mouths, eating stars and dust and whatever wandered too close. And yet, instead of turning inward in fear, humanity built probes to leave the cradle of the solar system and carry greetings to the unknown. The juxtaposition is striking. While nature builds silent one-way doors, we build tiny ships and push them outward with everything we know of love and sound and time. Voyager's path was carefully plotted to use gravity as a sling. In 1979, Voyager 1 swung past Jupiter, sending back the first close images of its storm bands and the volcanic eruptions on Io. In 1980, it flew past Saturn, catching the eerie pale rings and the haze of Titan's atmosphere. Voyager 2 took a different turn and went on to Uranus in 1986 and Neptune in 1989, glimpsing worlds no human eye had ever seen. Each time the spacecraft bent its trajectory with the planet's pull, stealing a little momentum, coasting faster into the void. Eventually, the sun itself became just another bright star behind them. As the spacecraft traveled, their radio voices weakened but never stopped. Decades later, they still speak in slow, faint codes across billions of kilometers. In August 2012, Voyager 1 crossed the boundary where the sun's influence gives way to the raw interstellar medium, the first human object to enter that space. Voyager 2 followed in 2018. Both now drift outward with no more planets ahead, only the long dark between stars. To think of these small craft gliding through a galaxy seeded with black holes is sobering and beautiful. They are utterly fragile, no thicker than a coin against the cold, and yet they endure. Bearing records of ocean waves and children's laughter past places where gravity crushes light, perhaps one day they will drift near some remnant of a star's death, a region where nothing returns. If so, the gold records and their etched maps will fall silent beyond an event horizon, swallowed like everything else. But until then, they move freely, an act of quiet rebellion against forgetting. When Carl Sagan spoke about the Voyagers, he often pointed out how small the chance was that anyone would ever find or understand them. That was not the point. The point was to say we were here and we cared enough to reach. Even while black holes promised erasure and physicists debated whether information could ever survive crossing that shadow line, we sent songs into the dark and let them go, knowing they might outlast Earth itself. In that act, there is something deeply human, the refusal to accept perfect silence, the longing to touch a future we cannot see. So as we picture black holes and their swallowing edges, it is worth remembering the opposite urge, the one that builds antennas and records and sends them sailing. Space can erase, but it can also carry. A star dies and collapses into a place where no message escapes. Yet across the same universe, a small craft can still whisper hello for thousands of centuries. The Voyagers are both fragile and stubborn, little proofs that exploration and hope can move outward, even as other regions pull everything in. In their faint ongoing call, we hear a reply to the cosmic trap, a statement that memory can leave home and maybe, somewhere, be found. As the last decades of the 20th century unfolded, astronomy underwent a quiet but profound transformation. Once the night sky had been a serene place of predictable lights. Stars rose and set, galaxies drifted slowly, and the dark between them seemed empty and safe. But with the spread of radio dishes, X-ray satellites, and eventually sensitive infrared and optical surveys that could sweep the heavens with digital eyes, that old calm began to break. Catalogs thickened with objects that looked wrong or behaved strangely. They were not points of light at all, but places where light vanished or twisted in ways no ordinary star could explain. What started with a few puzzling discoveries, Cygnus X1, the violently bright quasars far away, grew into a pattern too large to ignore. By the 1980s and 1990s, astronomers realized the universe was littered with candidates for black holes. Thousands upon thousands scattered across the maps. The first wave of evidence came from binary systems, a visible star dancing around an unseen partner, its light stretched and squeezed by orbital motion, its outer layers pulled off and heated to a furious glow in X-rays before falling away. Each system added one more possible black hole. It's usually a few times heavier than our sun, but squeezed into a sphere no bigger than a small city. These stellar mass black holes are the natural graves of giant stars, their formation understood through the physics of supernova collapse. Surveys with instruments like NASA's Rossi X-ray, Timing Explorer, and the European Space Agency's Integral found them by the dozen in our own galaxy and beyond, flickering in and out as their feeding disks changed. Yet even as these small but deadly objects were logged, stranger class emerged. Farther out, at the centers of galaxies, lurked engines on a scale almost unthinkable, millions to billions of solar masses. Crushed into volumes smaller than our solar system, quasars first identified in the 1960s as mysterious. Dazzling radio sources were now recognized as the brilliant feeding phases of supermassive black holes. When gas and dust fall toward such giants, the infall releases more energy than millions of suns, lighting up the cores of galaxies and outshining everything around them. Surveys with optical telescopes at Palomar and later the Sloan Digital Sky Survey traced these beacons across cosmic time, showing that in the early universe, quasars blazed everywhere, evidence of monstrous black holes forming quickly after the first galaxies appeared. Our own galaxy was not exempt. For a long time, the Milky Way's center was hidden from ordinary sight by clouds of gas and dust. But in the infrared and with clever radio techniques, astronomers began to peer through the veil. What they found was both elegant and unsettling. There, 26,000 light-years away in the constellation Sagittarius. Stars whipped around an invisible anchor with astonishing speeds. Andrea Ghez, in California, and Reinhard Genzel in Germany, spent decades tracking one especially useful star, known simply as S2. Its orbit nearly perfect, yet impossibly fast. Took just 16 years to loop around an unseen mass. By comparing its path year after year, they pinned down the mass of the hidden object, about 4 million times the Sun. Nothing else known to physics could be so heavy and so small, yet remain dark. Sagittarius A*, as radio astronomers had long nicknamed the Source, was revealed as a supermassive black hole, quiet now, but capable of devouring anything that wanders too near. This realization redrew our map of the cosmos. Instead of a tranquil star field, the Milky Way was a city with a dark gravitational downtown. Oh, Dell. Every star in slow orbit around a silent devourer, and if our home galaxy had such a heart, almost certainly others did too. Observations with the Hubble Space Telescope through the 1990s and 2000s confirmed it. Virtually every large galaxy seemed to hold a central black hole, its mass tied mysteriously to the size of the surrounding stellar bulge. It was as if galaxies and their central monsters had grown together, each shaping the other's destiny. The new sky surveys were not just lists, but portraits of danger and beauty. X-ray all-sky maps lit up with feeding binaries. Radio maps traced jets tens of thousands of light-years long blasting from galactic cores. Infrared images showed swarms of stars dancing in close, lethal proximity to invisible anchors. For the first time, humans could speak not just of isolated curiosities, but of a cosmic population. Black holes were not rare freaks. They were a fundamental feature of how the universe builds and destroys. Knowing this changed how astronomers told the story of matter itself. The small ones mark the end of massive stars, quiet records of explosions long past. The giant ones mark something deeper, a role in sculpting galaxies, triggering star formation when their outflows heat and compress gas, or quenching it when they blow too fiercely. The map of monsters was also a map of creation, paradoxically linking death and birth at grand scales, and all of it rests on subtle signs: the Doppler shifts of starlight, the time flicker of X-ray bursts, the patient plotting of orbits across decades. People like Ghez and Genzel spent nights atop Mauna Kea and in the Chilean desert, turning year after year, to watch single points of light move against the dense star field at the Milky Way's core. When they and their teams won the Nobel Prize in 2020, it felt less like the discovery of one object and more like the naming of a whole continent that had been there all along. Today, with instruments like Gaia Mapping Star, motions across the entire sky, and gravitational wave detectors hearing the far-off collisions of invisible masses, the map grows richer and stranger. We can almost chart where these monsters sleep, how many lurk unseen, and how their mergers send ripples through space-time itself. Yet for all the progress, each new black hole found is also a reminder of how little we know of what lies beyond that horizon. The map shows positions, weights, and orbits, but the interiors remain uncharted, perhaps uncharted. And so the universe we once thought a calm sea of stars now appears more like an ocean dotted with whirlpools, beautiful, powerful, and deeply unknown. The farther astronomers pushed their instruments, the more the universe seemed to respond by revealing tricks that let the invisible be glimpsed, if only indirectly. One of the most important of these tricks was something Einstein himself had predicted back in 1915, but doubted anyone would measure the bending of light by gravity. In his new theory, mass did not simply pull. It reshaped the very stage on which light travels. A ray passing near a heavy body should curve, not by force, but by following the warped geometry around it. The first test came in 1919 when Arthur Eddington sailed to the island of Principe, off West Africa, to watch a solar eclipse and measured starlight deflected by the sun. The result made headlines and turned Einstein into an icon. Yet that early demonstration was gentle. The sun's mass bends light only a tiny bit. Black holes promised a curvature so fierce that starlight could loop, arc, and smear into strange rings. By the late 20th century, astronomers were using this effect, now called gravitational lensing, as a way to hunt what cannot otherwise be seen. If a massive object lies between us and a distant star or galaxy, its gravity can bend and magnify the background light, distorting it into arcs, multiple images, or halos known as Einstein rings. This was first observed in dramatic form in 1979 when two identical images of a distant quasar were discovered on opposite sides of a foreground galaxy, one source. Two pictures, space itself acting like a lens. Over the next decades, huge surveys found lensing all over the sky. From giant galaxy clusters warping the shapes of even more distant galaxies to smaller, fleeting brightening events called microlensing, when a single star passes in front of another. Each lens told of hidden mass, sometimes ordinary, sometimes dark, and gave new ways to infer the weight of things. Unseen nowhere was this more powerful than at the very heart of our Milky Way. For much of the century, the galactic center remained a mystery, veiled by clouds of gas and dust that block visible light. Radio astronomers had named a bright, compact source Sagittarius A** in the 1970s, but its true nature was uncertain. By the 1990s, two rival groups, one led by Andrea Ghez at UCLA in California and another by Reinhard Genzel at the Max Planck Institute in Germany, set out to pierce that fog using adaptive optics and infrared detectors that could peer through the obscuration. They've built patient programs, returning year after year to track the tiny motions of stars crowded around the core, each one a brilliant point, fighting to be seen through the shimmering air of Earth's atmosphere. Among these stars, one stood out. S2, a hot blue star whipping around something unseen with astonishing speed. Beginning in the mid-1990s, both teams plotted its position night after night, measuring tiny shifts against the dense background. Over time, a clear, elegant orbit emerged, a long ellipse, completed in just 16 years. At its closest approach, S2 came within about 17 light-years of the center, just 3 times the distance between Pluto and the Sun, yet it circled something 4 million times heavier than the Sun itself. No cluster of stars could be so small and stable. No other known object could pack so much mass into so little space without shining. By the early 2000s, the case was overwhelming. At the Milky Way's core sits a supermassive black hole, quiet but undeniably present. The work was patient to the point of obsession. Instruments had to freeze the quivering of Earth's air, separating true starlight from blur. Positions were measured to precision smaller than the width of a coin seen from miles away. The teams published incremental updates as to moving here. S0 to 102, there reached step adding to a picture that no longer needed guesswork. When the two groups shared the Nobel Prize in 2020, it was recognition for decades of exacting craft, proof that by watching how gravity tosses and whips nearby stars, you can weigh something you cannot see and know it is real. For many, this was the first moment the black hole at the center of our own galaxy felt not like theory, but like a neighbor. The motions were graceful and terrifying. Stars hurtling at thousands of kilometers per second, yet held on a leash by an unseen master. There was also a quiet poetry in using light itself to prove the existence of something that traps light. Gravitational lensing and precise orbit. Tracing turned the black hole from an abstraction into a measured fact. Beyond our galaxy, similar methods expanded the senses. Astronomers measured how fast gas spun near galactic cores, how broad emission lines became under intense gravity, how central masses warped starlight behind them. Even though no one could look past an event horizon, these signatures became a kind of seeing. You could read the shape of the invisible by how it bent its surroundings. This edge of seeing is where physics meets patience. No photograph could show Sagittarius A** swallowing stars, yet the slow dance of S2 and its companions drew a perfect map of the monster's gravity. Light curved, time stretched, and though the core itself remained black, its presence could be drawn as clearly as if it were lit, to follow those faint, precise motions across 20 or 30 years is to accept a human timescale matched against the heartbeat of a galaxy, and to know that even the darkest places leave clues if you watch long enough. The story of the galactic center is also a story of human curiosity meeting deep silence. As we send out Voyagers with their hopeful records, we also aim our finest instruments toward a region where nothing returns. And yet, by tracking tiny changes in starlight and subtle arcs of lensing, we turn that silence into knowledge. The black hole remains unseen, but it can no longer hide. Its gravity writes its signature in the paths of nearby stars, and patient eyes have learned how to read by the early 1970s. Black holes had moved from mathematical curiosities to objects astronomers were forced to accept as real. Yet there remained a deep, almost philosophical unease about what they meant. According to classical general relativity, a black hole was the perfect trap. It could grow, it could merge with others, but it could never give back anything of what it had taken. It was a one-way process, and too many physicists, that finality seemed to break the spirit of physics itself. A field built on the idea that every interaction can, in principle, be undone if you know enough. Among those unsettled by the notion of absolute loss was a young British theorist named Stephen Hawking. Working in Cambridge, thin and sharp-minded, his body already showing the first cruel signs of the motor neuron disease that would one day confine him to a wheelchair and a synthetic voice. In 1974, Hawking published a result so surprising that even he tried at first to disprove it. Black holes, he said, were not perfectly black after all. Hawking's argument grew from an attempt to bring quantum mechanics, the physics of the very small, into conversation with Einstein's smooth, continuous spacetime. In quantum theory, the vacuum is never truly empty. Instead, it seethes with momentary flickers. Pairs of particles and antiparticles spring into existence and vanish almost instantly, borrowing energy for the briefest time before returning it, a constant jitter known as quantum fluctuation. Normally, these pairs annihilate and leave no trace. But near the event horizon of a black hole, the stage is warped enough to change the story. Hawking realized that if such a pair pops into existence just at the edge, one particle might slip across the horizon while its partner escapes outward before they can cancel each other. To an outside observer, the escaped particle looks as though it was emitted. By the black hole itself, this process would have astonishing consequences. The black hole appears to glow faintly, giving off what we now call Hawking radiation. It is not a thermal light you could photograph with a camera. The temperature is unimaginably low for any black hole. It's larger than a mountain, but in principle, it is real. Energy leaving the black hole means it slowly loses mass, because in Einstein's universe, mass and energy are the same currency. Over unfathomable times, far longer than the current age of the cosmos, the black hole would shrink and eventually vanish. The perfect trap would, at the end of an inconceivably long story, evaporate into a puff of light and particles. Hawking's calculation was careful but radical, and it collided head-on with the older picture of eternal, silent black holes. At first, many physicists were skeptical. The idea that quantum fields and curved space could combine this way was not fully developed. Hawking himself doubted his result when the math first led there, but every check he made seemed to confirm it. By the late 1970s, after debates at conferences and quiet work by colleagues like Kip Thorne and Jacob Bekenstein, the community accepted Hawking radiation as one of the first windows into what a future theory of quantum gravity might look like. Black holes were no longer absolute graves. They had a kind of slow, cold breath. The implications reached far beyond astronomy. If black holes can radiate, then the universe does not simply hide everything behind an event horizon forever. Yet the way the radiation carries energy but seems to forget almost all detail about what fell in sparked a fierce puzzle, now called the information paradox. According to quantum theory, information cannot be destroyed. Yet Hawking radiation appears to be random, telling nothing of the star or planet or signal that once crossed the horizon. Physicists have wrestled with this paradox ever since. From string theory proposals to the holographic principle, suggesting that all the lost information might be stored on the horizon's surface like a cosmic ledger. Even today, though Hawking radiation is ghostly and weak, a black hole the mass of the Sun would take a time about 10 to the 67th power years to evaporate, a number so large it defies real imagination. Billions upon billions of times longer than the universe has existed. Supermassive black holes like Sagittarius A** would last even longer, outliving stars and galaxies, glowing only faintly as the cosmos cools and dims. Only tiny, hypothetical black holes formed in the Big Bang might radiate fast enough to die within a human timescale, but none have yet been seen. Still, the idea that black holes are not eternal shifted how scientists thought of them. They were no longer simple tombs, but actors with life cycles, however stretched. They could form, grow by feeding and merging, and then, in the farthest future, fade away. The dark would not last forever. Even the heaviest giants would end as a whisper of quantum light. For a species just learning to map these monsters, it was an extraordinary thought. The universe's most fearsome destroyers are themselves impermanent, ruled not just by gravity, but by the small, restless rules of the quantum world. Hawking's insight also changed culture. The image of a black hole quietly leaking away, undone by its own horizon, caught the public's imagination and brought abstract physics into everyday conversation. It reminded people that mystery and beauty lie not just in vast explosions, but in the invisible grain of reality, where tiny virtual particles decide the fate of cosmic giants. Hawking himself, with his humor and his machine voice, became a symbol of curiosity defying limits. A man who stared at the cold heart of space and found it stranger and less final than anyone guessed, even though no telescope has directly seen. Hawking radiation, it is far too faint against the cosmic background. The idea continues to guide experiments. Physicists build analog black holes in laboratories using sound waves in fluids or light in special media, hoping to detect similar quantum leakage. Particle accelerators and gravitational wave studies indirectly test pieces of the theory. Each effort is a way of touching an insight born in 1974, when one man sitting in Cambridge dared to ask what quantum jitter means at the edge of no return. Thus, the fire of Hawking is a quiet one. It does not blaze like a supernova, but it alters the destiny of every black hole and perhaps of the universe itself. It says that even the deepest dark is not absolute, that over enough time, even perfect traps let go. And it marks one of the most astonishing human achievements: to reason our way to the fate of things no eye can ever see, guided only by equations and imagination. By the time the idea of Hawking radiation had settled into the scientific world, another deeper problem rose up from it like a shadow. At first, it seemed almost philosophical, something you might debate late at night over coffee. But soon it became clear that the question touched the foundations of physics itself. The puzzle was simple to state, but frightening to follow. If a black hole can slowly leak away and vanish, as Hawking showed, then what happens to the things it swallowed? Where do the details go, not just the mass and the charge and the spin, which we know are carried outward, but the intricate information about everything that once fell past the horizon? The shape of atoms, the tangle of quantum states, the arrangements of matter and light. Physics for centuries had assumed that such information is never truly destroyed. You can mix it, hide it, scramble it beyond recognition, but somewhere the record exists. Hawking's results seem to say otherwise. To understand why this cuts so deeply, you have to step back into the rules that underlie quantum mechanics. One of its central features is unitarity. The notion that the evolution of a closed system preserves the complete description of its state. If you know exactly how a set of particles starts and how they interact, in principle, you can wind the movie forward or backward. No information is lost, even if it is wildly scrambled. This idea is tied to energy conservation and to the deep symmetry that keeps physics coherent. Lose unitarity, and you risk losing predictability itself. Yet Hawking's calculation, done carefully with quantum fields on the curved space-time of a black hole, produced radiation that looked perfectly thermal, random. carrying only the simplest facts about the black hole, but none of the story of what formed it. Drop in a diamond or a library or an entire planet, and when the whole finally evaporates, the outgoing light is just dull, featureless heat. The universe would have forgotten. At first, Hawking himself was comfortable with this conclusion. He said the event horizon really does break the chain of information, that black holes are like cosmic shredders. Others were not so ready to accept that. John Preskill at Caltech, Leonard Susskind at Stanford, Gerard T. Hooft in the Netherlands. These and many others fought back. They argued that even though Hawking's calculation was brilliant, it was incomplete because it did not yet include a full quantum theory of gravity, something no one had built. In their view, nature must have a way to encode and return the data, even if we cannot see how. This debate, which began in the 1970s and sharpened through the 1980s and 1990s, became known as the black hole information paradox. It was not only an academic fight. It shaped how physicists searched for a unified theory. String theory, for instance, found new urgency in part because it offered hints that black holes might have microscopic bits or strings whose states could count and preserve information. In 1997, a mathematical bridge between gravity and a volume and a quantum field theory on its boundary? In that picture, nothing in the bulk, not even inside a black hole, truly destroys information. It is somehow recorded on the surface like a hologram. This idea, the holographic principle, grew partly from the need to resolve Hawking's disturbing conclusion. The paradox also spilled into philosophy. If black holes truly delete information, then determinism, the idea that the present completely determines the future, breaks. You could not, even with infinite precision, reconstruct what once existed if it had passed the horizon. For a universe that seems to obey deep conservation laws, this was alarming. It suggested a fundamental unpredictability, not just in practice, but in principle. A tear in the elegant clockwork vision that has driven science since Newton. The argument went public in a famous way in 1997. When Hawking and Kip Thorne made a bet with Preskill, they wagered that information is indeed lost in black holes. Preskill bet that it is preserved. For years, the black hole community wore t-shirts and traded playful insults at conferences. But underneath was serious work. String theorists counting the quantum states of certain black holes, trying to show that entropy, the measure of disorder, matched the area of the horizon and could be explained by microstructure. Slowly, evidence accumulated that maybe the pessimists were wrong. In 2004, Hawking surprised the world by conceding the bet and admitting that he now believed information could, in principle, escape or be recovered. Though the exact mechanism remained obscure, yet even this resolution is not simple or fully accepted. We still do not have a clear practical way to see how the data comes back. Some propose that the radiation is not perfectly random, that subtle correlations, too faint to notice but real, encode the story of what fell in. Others imagine the horizon itself as a kind of quantum surface where everything that enters gets painted and later released. Still others have proposed dramatic features like firewalls, violent energy barriers at the edge that would rewrite the smooth story of general relativity to protect information. Each path tries to honor both quantum mechanics and gravity without breaking either, but none is final. What makes the information puzzle so powerful is how it turns a remote, unreachable object into a test of the deepest principles we have. A black hole, thousands or billions of light years away, can force us to ask whether the universe keeps its books balanced. It has changed the meaning of an event horizon from simply a border of no, returned to a laboratory for ideas at the edge of known science. Graduate students and Nobel laureates alike wrestle with it. Whole conferences are devoted to questions first framed in the wake of Hawking's 1974 paper. For anyone outside physics, the puzzle also has a strange emotional weight. We are creatures who try to remember. We build libraries and send records on spacecraft because we hope nothing is entirely lost. To think of a place where the past can vanish seems to wound that hope. And yet the resistance to that idea, the decades of clever attempts to prove that memory somehow survives, even in the darkest Traps is also deeply human. It is as if the universe itself is being asked to honor its own history. So the information paradox stands not just as a technical debate, but as a symbol of curiosity and defiance. It began with one quiet calculation in Cambridge and spread outward to reshape fields from quantum theory to cosmology. It remains unsolved in many details. But it has already done something extraordinary. It has forced us to ask whether reality forgets. And in doing so, it has taught us how fiercely we want the answer to be no. For most of the 20th century, the idea that space and time themselves could ripple like the surface of a pond felt almost too poetic to be real. Albert Einstein had predicted such waves in 1916 as a quiet side note to his general theory of relativity. But he doubted they would ever be detected because their effect seemed so faint. Space is astonishingly stiff. Only the most violent cosmic events could shake it enough for the tremor to reach us. And even then, the signal would be smaller than the width of a proton over kilometers of distance. Yet decades of theory and slow technological progress built toward one extraordinary September morning in 2015, when an instrument buried in the quiet farmlands of Louisiana and mirrored in the hills of Washington caught a sound from the deep past, a quick, rising chirp that began below human hearing and swept up into the range of audio like the faint pluck of a string. It was the voice of two black holes colliding. The experiment that heard it was called LIGO, the Laser Interferometer. Gravitational Wave Observatory, a pair of L-shaped detectors, each arm for kilometers long, lined with vacuum tubes and polished mirrors, suspended by fibers thinner than a human hair. A laser beam split and sent down the two arms, bounced back and forth hundreds of times. If a gravitational wave passed through, one arm would stretch and the other squeeze by a fraction of an atom, shifting the pattern of light when the beams met again. To register such tiny changes, the system had to be isolated from trucks, earthquakes, even the faint pull of the moon. Engineers and physicists spent decades chasing this dream, with early versions of LIGO running in the 2000s, but never quite sensitive enough to catch a signal. Then came a major upgrade. Advanced LIGO, finished just weeks before the September detection, tuning the ears of Earth to a new level of quiet. On September 14th, 2015, at 9 hours 50 minutes and 45 seconds UTC, the two detectors, one in Hanford, Washington, and one in Livingston, Louisiana, saw nearly identical blips separated by 7 milliseconds, the time it takes light to travel between them. Analysis showed the signal matched the final seconds of two black holes spiraling together, one about 36 times the mass of the Sun, the other about 29. They had danced for billions of years, somewhere 1.3 billion light-years away, their orbits shrinking as gravitational waves carried away energy, until finally they collided and merged into a single black hole, about 62 solar masses. The leftover mass radiated away as pure gravitational energy. For a fraction of a second, that collision released more power than all the stars in the observable universe combined. When the LIGO team, Key, announced the result on February 11, 2016, the room erupted. People who had devoted entire careers to chasing vibrations smaller than imagination now had proof that the universe was alive with them. The signal was unmistakable, a smooth rising tone in frequency and amplitude, exactly as relativity predicted for black holes merging. Einstein's century-old idea had become an observable fact. More than that, a new sense had opened. Until then, astronomy had been limited to light, visible, radio, infrared, X-ray, gamma. Now, humans could listen to space-time itself. The emotional weight of that first detection was enormous. Scientists played the data converted to sound, a chirp lasting just 0.2 of a second, and realized they were hearing the death cry of two ancient monsters. The event was named GW150914, a bland code that could not capture the wonder of what it meant. Over the next few years, LIGO and its European partner Virgo found more black holes of unexpected sizes, some heavier than theory predicted, colliding out in the dark. Each detection added a new pin to the map of the universe's violent past and challenged models of how massive stars die and pair up, Gravitational waves offered more than just confirmation. They gave astronomers a way to measure distance and expansion directly, because the waves carry their own calibration. They allowed tests of relativity in realms of extreme gravity never before probed. When neutron stars merged in 2017, LIGO and Virgo caught the signal, and telescopes worldwide swung to watch the afterglow in light, proving these collisions forge heavy elements like gold and platinum. But it was the black hole mergers that felt most like pure discovery, invisible giants crashing together with no light. No electromagnetic whisper, and yet we could know. 4 black holes, which by definition hide behind horizons. This was revolutionary. Light cannot escape them, but their dance before merging shakes the universe itself. The waves pass untouched through intervening matter, arriving at Earth as clean records of mass, spin, and orbit. By analyzing the waveforms, scientists can weigh black holes and trace their history. Were they born of single stars or earlier black holes? Did they spin fast or slow? We can now survey populations across cosmic time without needing them to shine. The technology also inspired a new way of thinking about exploration. Just as radio telescopes opened invisible skies in the 1930s, gravitational wave observatories are teaching us to feel rather than see. Plans are already in motion for bigger detectors, Lisa. A space-based interferometer with 3 satellites, millions of kilometers apart. Scheduled for the 2030s, will catch waves from supermassive black holes colliding as galaxies merge. Einstein telescope and cosmic explorer on Earth will hear fainter signals from deeper space. It is as if we have just dipped a hydrophone into a dark ocean and realized it is full of songs. That first chirp in 2015 did more than confirm a prediction. It changed how we think about black holes. No longer purely silent tombs, they are now known to be musicians of a sort, shaking the very fabric of reality when they meet. Each wave that arrives carries news from epochs before humans, before Earth's continents. Before the sun, they travel unbroken across billions of light years. Threads of pure geometry telling us that even in the most hidden places, the universe still leaves a trace. For a long time, black holes were feared as ultimate erasers, places where matter and history end. Gravitational waves suggest a gentler truth. The act of swallowing and merging is not completely private. The dark may be deep, but it is not mute. In the quiet forests of Louisiana and the wide plains of Washington, humanity learned to hear that whisper. And in doing so, gained not just a new instrument, but a new kind of sight. Each echo from the dark adds to our map. Each tiny ripple stretches imagination. And each detection is a reminder that the universe's secrets, no matter how silent, still find ways to reach us. For centuries, the idea of a black hole was something that could only be spoken about in the language of theory, a picture drawn in equations rather than in light, because by definition, it seemed impossible to ever truly see one. Astronomers could measure the motions of stars. They could observe X-ray flares from disks of matter spiraling inward. They could trace radio jets fired from the poles of active galaxies. But the heart of the black hole itself remained hidden. The event horizon was not a surface you could photograph. It was a border beyond which all signals vanished. Still, the dream of capturing an image of that shadow persisted. And by the early 21st century, a daring collaboration of scientists believed they had found a way to do it. They would not build a single telescope, but instead link many scattered across Earth, synchronizing them so precisely that together they would act as one instrument the size of the planet itself. This was the Event Horizon Telescope, or EHT, an international project that brought together observatories from deserts, mountaintops, and frozen plateaus. Each station was equipped with highly sensitive radio receivers tuned to millimeter wavelengths, capable of detecting the faint signals emitted by hot gas whirling just outside a black hole's horizon. To make them act as one telescope, atomic clocks called hydrogen masers kept time to within a billionth of a second, so that when the data was combined later, the interference patterns could be reconstructed into an image. In 2017, during a week of favorable weather, the team pointed this Earth-sized eye toward 2 targets, the giant at the core of our Milky Way, Sagittarius A*, and the even larger black hole at the center of the galaxy M87. 55 million light-years away. The data gathered on hard drives by the petabyte was shipped physically by airplane from each station to 2 central processing centers in Massachusetts and Germany. For months, then years, teams of scientists worked on calibration, alignment, and imaging, testing algorithms, cross-checking, and making sure every step was free from bias. The anticipation grew almost unbearable. For decades, people had drawn artistic impressions of what a black hole might look like, usually a glowing ring around a dark core, but no one knew how close reality would come. When the first images finally emerged from the data in early 2019, those who saw them described the experience as surreal, almost disorienting, because for the first time, human beings had looked directly at the silhouette of a black hole. On April 10th, 2019, the image was unveiled to the world, a lopsided ring of golden light encircling a dark circle, the shadow of M87*. The black hole itself was 6.5 billion times the mass of the Sun, large enough that its event horizon spanned more than the size of our solar system. Yet appearing on Earth's sky smaller than a pinprick, the image was grainy, the resolution limited, but it carried a power beyond detail. It was proof, not by inference or deduction, but by direct vision, that these monsters truly exist. The ring of light was emission from gas heated to billions of degrees as it circled the horizon. The dark center was the place from which nothing returned. The announcement was broadcast around the world, with simultaneous press conferences held in Washington, Brussels, Santiago, Shanghai, and Tokyo. The scientists who spoke seemed both proud and humbled, their voices breaking slightly as they described years of effort by more than 200 researchers in over 20 countries. They knew they were presenting something that would appear in textbooks and museum halls for generations. An image that would join the handful of iconic photographs, Earth rising over the moon, the pale blue dot of Voyager, that change how we see ourselves. Stephen Hawking had once written that black holes might not be so black after all. And now here is the visible evidence of their outline. Captured by radio light and human patience, what made the image so moving was its combination of strangeness and familiarity. It looked much like the simulations that had been made over the years, with the ring brighter on one side due to the Doppler effect of matter moving toward us, and yet to see it rendered from real data. From photons that had traveled 55 million years only to be caught in a telescope dish on Earth, gave it an undeniable weight. The black hole was no longer an abstraction. It was an object in the sky with a face we could recognize. For the EHT scientists, the work was not finished with that release. The data on Sagittarius A** was more complicated. Because the smaller black hole at our own galactic center changes too quickly, its gas swirling in minutes rather than days, blurring the picture. But the success of M87** proved that the method works. That with enough telescopes and enough coordination we can pierce even the deepest shadows. Plans were already underway to expand the array to add stations in Africa and space. To sharpen the view and capture movies of matter in motion around horizons, looking back, the unveiling of M87** felt like a threshold moment in human history, as if a new sense had opened. For centuries we had wondered what it would mean to look into the abyss. Now we know. It is not empty, not mystical, but a ring of fire around an absence. Structure described by mathematics, yet revealed in light. The shadow image reminded us that the universe is not only vast, but intimate. That with ingenuity and collaboration, we can make the invisible visible. And in that ring of light, bent and twisted by gravity, there was something both alien and strangely beautiful, a mirror held up to our own urge to see. The abyss had given us a face, and for the first time, we looked back. At first glance, nothing should come out of a black hole. The whole idea of the event horizon is that it is a place of no return, a region where even light is trapped. Yet as astronomers began to look more closely at the regions just outside those horizons, they found some of the most powerful and beautiful displays of energy in the entire universe. Instead of perfect silence, many black holes are surrounded by violent engines that hurl matter outward in long, narrow beams, jets that can stretch for thousands or even millions of light years. These jets are among the brightest objects in the sky when seen at radio or X-ray wavelengths, and they have forced scientists to rethink what it means for something to be a perfect trap. Nothing escapes once it crosses the horizon. But the space just outside is a cauldron where forces beyond imagination are at play. The process begins with feeding. Black holes rarely drift empty through space. They often have companions, or find themselves embedded in regions rich with gas and dust. As material is pulled inward by gravity, it does not fall straight in. Instead, it gathers into a flattened, spinning accretion disk. Friction within this disk heats the infalling gas to incredible temperatures, tens of millions of degrees, until it shines in X-rays and gamma rays. At the same time, the spinning and the ionized plasma generate powerful magnetic fields. These fields twist and coil as the disk rotates, winding up like invisible springs under immense stress. In certain conditions, those magnetic structures channel some of the inflowing matter away from the hole's mouth and fling it outward along the rotation axis at speeds close to light. This is one of the deepest paradoxes of black hole physics. The very act of falling in can drive escape for a small fraction of the material. The jets are not made of matter pulled from inside the event horizon. Nothing crosses back once it's gone, but from the chaotic, superheated region just outside. As magnetic fields snap and reconnect, they launch narrow streams of plasma that stay astonishingly collimated across distances where any ordinary beam would scatter. These outflows can punch through whole galaxies, carrying energy far from the central engine, sometimes shutting down star formation by heating or sweeping away gas. Other times, compressing gas and triggering new births of stars. One of the best-known laboratories for studying this phenomenon is the giant black hole in M87. The same object the Event Horizon Telescope imaged in 2019, long before its shadow was captured. MAD-7 was famous for a brilliant jet visible even in optical light. Discovered in 1918 by astronomer Heber Curtis, that single beam, more than 5,000 light-years long, shoots from the galaxy's core with energy so intense they light up the radio spectrum and can be seen in X-rays. In our own Milky Way, smaller but still powerful jets erupt from systems like GRS 1915 plus 105, where a stellar mass black hole feeds on a companion star, producing bursts that flicker and fade on timescales of minutes, 2 hours. The exact physics of jet launching remains an active frontier. One leading idea, proposed by Roger Blandford and Roman Znayak in 1977, is that a spinning black hole can transfer some of its rotational energy to the magnetic fields threading its horizon. This Blandford-Znayak mechanism suggests that the hole's own spin, twisted up with the disk's fields, powers the jets. Other models focus on the inner accretion flow and how turbulence and magnetic reconnection fling material out. Whatever the details, observations have confirmed that the most extreme jets come from the fastest spinning, most actively feeding black holes. Seeing these jets forces a shift in how we picture black holes. They are not simply dark sinks, but engines of change for their surroundings. Entire galaxies bear the marks of these outflows. The giant radio lobes that stretch hundreds of thousands of light-years from active galaxies are relics of past jet activity, inflated by particles accelerated to near light speed. These lobes glow for millions of years, long after the central black hole may have quieted. In galaxy clusters, jets carve vast cavities in hot gas, detectable by X-ray telescopes like Chandra. The famous Perseus cluster shows ghostly bubbles blown by a central black hole, each bubble larger than our entire Milky Way. There is also a human element to how we have uncovered these wonders. Radio astronomers in the mid-20th century puzzled over bright, seemingly star-like sources until they realized they were galaxies with jets aimed roughly in our direction, their light amplified by relativistic effects. The term quasar came from these discoveries. Later, X-ray missions like Rosat, Chandra, and Examemnoten revealed the cores of these systems in fine detail. While the Hubble Space Telescope caught optical glimpses of the jets themselves, today, networks of telescopes watch jets flare and fade in real time, tracing how black holes feed and expel. For all their violence, there is a strange order to jets. They emerge in pairs, aligned along the black hole's spin axis. Symmetrical, though rarely equally bright because of relativistic beaming, the forward jet appears brighter to us if it points our way. They remain astonishingly narrow across distances where you would expect them to scatter, a testament to the power of magnetic confinement, and they can switch on and off as feeding rates change, showing that black holes are not permanently active but have cycles of hunger and quiet. To witness such cosmic fireworks erupt from the edge of ultimate darkness is to understand that black holes are not endpoints alone. They influence their environment on every scale, from the immediate neighborhood wherein falling matter is torn apart, to whole galaxies where jets sculpt structure and control growth. The light we see from them is indirect but dramatic, proof that while nothing escapes the horizon, the space just outside can be as bright and alive as any star. For humans looking up, jets are also a kind of reassurance. They remind us that even the darkest forces in the universe have edges where energy and light still exist. They show that the story of a black hole is not only about swallowing, but also about giving back. In forms so powerful they can cross millions of light years and still be seen by fragile instruments on a small blue planet. In that paradox of darkness feeding light lies some of the most haunting beauty astronomy has ever found. For most of human history, falling was a simple thing. We drop an object, and it hits the ground. We leap from a step, and our feet meet something solid. But to fall into a black hole is to step outside that ordinary idea. There is no floor waiting, no clear landing where you could pause and look around. Instead, there is a continuous deepening, an approach to something that seems like a center, but may not exist in any familiar way. And the very notion of time and space begins to slide. Apart as you go, imagine an astronaut drifting toward a stellar mass black hole, perhaps 10 times the mass of the Sun. From far away, their journey looks almost normal at first. They circle closer, drawn by gravity, engines long since cut because no fuel could compete with the pull. The stars behind them bend slightly as their light is deflected. The black hole itself appears not as a ball, but as a dark, perfect void where the starfield warps and loops around an invisible edge. Closer still, the force of gravity begins to change across their body. Their feet are nearer to the hole and pulled harder than their head. This difference is tiny at first, but grows as they approach. This is tidal gravity, the same stretching and squeezing that moves our oceans, but magnified beyond reason. Eventually, it would become lethal, pulling their body into a thin filament, what physicists, with a trace of dark humor, call spaghettification. Bones, muscles, atoms themselves would be torn along the direction of fall and squeezed sideways. No material we know could resist once the difference in pull between head and toe rises to millions or billions of Gs. Yet from the astronaut's own viewpoint, something curious happens. They feel the stretching, but not the event horizon itself. There is no visible sign when they pass that invisible boundary. No flash, no sudden barrier. The crossing is smooth because the horizon is not a physical surface, but a place defined by light's inability to escape. Their clock ticks normally. Their heartbeat stays steady. They keep falling as though through empty space. But to anyone watching from a safe distance, the picture is wildly different. The outside observer sees the astronauts slow and fade, their signals redshifted into longer and longer wavelengths, light stretched thin until it vanishes. In principle, the image of their final approach would hover forever, just above the horizon, frozen in time. Though in practice, the light would dim beyond detection long before that. If the black hole is small, like a few solar masses, the tidal forces become deadly well before the horizon itself. In that case, spaghettification ends the story quickly. But for a supermassive black hole, the kind that anchors galaxies and weighs millions or billions of suns, the horizon is so vast and the gradient of gravity so gentle there that an astronaut could drift across intact, unaware of passing any threshold. They could, in theory, survive for a while after crossing, though only they would know it. No word, no signal could come back. Inside, the pull grows stronger as the radius shrinks, and eventually no known force could resist. but the exact end is a question physics still cannot answer with certainty. General relativity predicts a singularity, a point where density and curvature go infinite, but quantum theory says infinities are signs of incomplete understanding. Some propose that space and time may loop or smear out, that a new description of reality would take over long before infinite collapse. What is sure is that time itself behaves strangely. To the astronaut, clocks tick normally. They might see the entire external universe race forward in the final seconds before crossing. Though the details depend on the precise path, to the distant universe the astronaut's time slows and then stops at the horizon. These two perspectives can coexist without contradiction because relativity allows time to be personal, tied to each path through space. It is one of the most unsettling aspects of black holes, that falling in is both ordinary and final. A trip that feels continuous but ends in unobservable regions. Scientists have tried to model what the interior might be like. Some speak of an inevitable singularity where all paths meet, others of a Planck core where quantum gravity takes over. Some speculate about bounces or bridges to other universes, though there is no evidence such paths exist. What we know for certain is limited to the approach, the warping of light, the stretching of space, the tidal pull that grows without mercy. Beyond the horizon, we can only follow equations into unknown territory. Stories about falling in also teach something subtle about black holes. They are not cosmic vacuum cleaners sucking from infinite distance. An astronaut far away could orbit safely. And even near the hole, a strong enough engine could let them escape if they act before crossing the horizon. The point of no return is real, but not everywhere. It is a boundary you must cross to be lost. The thought experiment of such a fall has shaped entire fields of physics. Kip Thorne and John Wheeler used it to teach generations of students. Science writers have turned it into vivid journeys. Artists have tried to paint what it might look like to look up and see the universe distorted into a thin ring above. And while no one will ever return from such a voyage to report what lies past the horizon, the act of imagining it has driven progress from understanding tidal forces to debating quantum fate. In the end, to fall into a black hole is to let go of all ordinary anchors. There is no bottom as we know it, only a deepening curvature where our current laws reach their edge. The astronaut's story ends not with a crash, but with silence. A drift into a region cut off from all future contact with the outer world. Yet the very fact that we can describe so much of that journey, the stretching, the slowing of time, the way light bows and twists, is a triumph of human thought. We have learned to follow math and imagination into a place no signal can return from, and to know, with remarkable certainty, what the first stages of that descent would be like. Beyond that, the mystery remains, and perhaps that is part of the fascination. The fall that never reaches a floor. The horizon that can be crossed but never undone. When scientists first faced the strange geometry of black holes, it was almost impossible not to wonder if these pits in space might also be doors. The equations of general relativity do not just allow a region where gravity traps light. Under certain conditions, they also suggest curious passages that connect distant places or even separate universes. In 1935, Albert Einstein and his collaborator Nathan Rosen published a short paper exploring what happened if you extended the mathematics of the Schwarzschild solution instead of stopping at the singularity. They found that two identical exterior regions could be joined by a throat, a smooth tunnel through space-time. Later, these came to be called Einstein-Rosen bridges, though today we know them by the more evocative name wormholes. The idea was tantalizing. Maybe a black hole was not only an end, but also an entrance. From the start, however, the picture was fragile. The original Einstein-Rosen bridge pinched shut too fast for anything to pass through. It was like a tunnel that collapses the instant you try to enter. To keep it open, you would need matter with negative energy density, something not known to exist in macroscopic amounts. In the 1950s and 1960s, physicists like John Wheeler, who coined the term wormhole, and later Kip Thorne and Michael Morris played with the equations, asking what kind of exotic stuff, called exotic matter for lack of a better word, might prop the throat open long enough to travel. Their calculations showed that if such negative energy could be arranged, a stable, traversable wormhole might exist. But the requirements seemed implausible. All known forms of matter and energy have positive density and resist rather than invite passage at the same time. Another speculative cousin appeared, the white hole. Mathematically, if you take the time reversal of a black hole, you get an object from which nothing can enter but matter and light can only leave. A white hole would be like a cosmic fountain, pouring out energy without letting anything in. Some solutions to Einstein's equations seem to pair black and white holes, with the bridge between them acting as a conduit. Yet no evidence for white holes has ever been found. And most physicists suspect they are artifacts of idealized conditions that real stars and galaxies cannot produce. Still, the symmetry is beautiful and difficult to ignore. In the late 20th century, as quantum mechanics and relativity were pushed to live together more comfortably, wormholes returned in another guise. Stephen Hawking speculated about quantum foam, a wildly fluctuating space-time on the smallest scales, full of tiny wormholes popping in and out of existence. These would be microscopic and fleeting. It's not tunnels for spaceships, but hints that space-time is more dynamic and interconnected than our smooth maps suggest. Others propose that if such tiny bridges could be stabilized, perhaps through unknown high-energy physics, they could expand or be threaded into useful shapes. Science fiction eagerly seized on these visions. Novels and films, from Carl Sagan's Contact to Christopher Nolan's Interstellar, have used wormholes as narrative bridges across impossible distances. Kip Thorne himself, a technical advisor for Interstellar, helped ensure the movie's wormhole obeyed at least the spirit of known physics. Yet despite the allure, each attempt to make wormholes practical runs into barriers. Negative energy does exist in a limited sense. The Casimir effect between metal plates shows. The vacuum can have regions of lower than normal energy, but only in tiny, fragile amounts, not enough to hold open a tunnel through space. Quantum instability also plagues these structures. Calculations show that once you try to enlarge a wormhole, quantum fluctuations tend to build up and destroy it. And even if one could survive causality, the rule that effects follow causes may break, opening the door to time travel paradoxes. Some researchers think nature forbids stable, traversable wormholes precisely to protect causality and avoid contradictions. Still, speculation continues because wormholes sit at the crossroads of what we want most: a bridge between relativity and quantum theory, and a tool to explore deep questions about space, time, and information. In recent years, new work inspired by holography and quantum entanglement has given them fresh life. Juan Meldacena and Leonard Susskind suggested a link known as equals EPR, proposing that every pair of entangled particles might be connected by a tiny non-traversable wormhole. This idea does not allow travel, but it hints that the geometry of space-time could emerge from the fabric of quantum connections. Such thinking could be a path toward quantum gravity, elusive theory uniting the very large and the very small. The contrast between rigorous science and hopeful imagination is sharp here. Observers have mapped black holes, weighed them, and even imaged their shadows, but no observation points to an open passage. We know how to describe the warping that creates horizons, but not how to twist that warping into a usable bridge. Yet the fact that the equations leave room for the possibility keeps the idea alive. When you write down the mathematics of general relativity, nothing in the pure form of the theory forbids shortcuts. It is the physical content, the types of energy and matter we know, that seems to block them. If future physics finds new states of matter or new symmetries, what is impossible now might shift in this way. Wormholes are less a promise than an invitation. They remind us that black holes are not just cold, dead ends, but part of a much stranger landscape. They encourage thought experiments about travel, causality, and even the nature of memory. Could information swallowed in one place reappear elsewhere? Could a dying star create not only a hole, but a hidden doorway? No one can say with certainty, and perhaps that is the point. The wild ideas live on the edge of proven knowledge, where curiosity is strongest. For the moment, the universe offers only dark horizons, not luminous tunnels. But the pursuit of these hypothetical bridges has sharpened our understanding of gravity and quantum fields, pushed new generations of physicists to test the limits of both, and kept alive one of humanity's oldest longings, that somewhere, somehow, there might be a way through the dark rather than only into it. When black holes first became accepted as real, as objects rather than mathematical curiosities, one of their strangest qualities was how gentle they seemed at the horizon. Einstein's equations and the work of later relativists suggested that an astronaut drifting across would feel nothing unusual in that instant. The event horizon was supposed to be a quiet, locally unremarkable surface. All the drama happened later, deeper inside, where gravity rose to lethal strength. This peaceful view came to be called the no-drama principle, and for decades, it was a comfortable part of the black hole story. But as physicists pushed harder on the question of information, whether the universe truly keeps track of what falls in, cracks appeared in that serene picture. By the early 2010s, a new and deeply unsettling idea surfaced. Maybe the horizon is not smooth at all. Maybe it is a blazing barrier of energy, a firewall, waiting to incinerate anything that tries to cross. The seed of this proposal lay in the very debates Stephen Hawking had sparked about information loss. If a black hole radiates and eventually evaporates, then something subtle must encode the details of what it has swallowed into the outgoing Hawking radiation. Quantum mechanics says that information cannot be destroyed. The final radiation must be entangled in just the right way to preserve the story of everything that went in. Yet when theorists tried to work out that entanglement carefully, contradictions emerged. In 2012, Ahmed El-Hiri, Donald Morelf, Joseph Polchinski, and James Sully, four theoretical physicists often referred to by the shorthand AMPS, wrote a paper pointing to an apparent conflict among three things scientists wanted to hold true. First, that quantum information is never lost. Second, that an observer falling into a black hole experiences nothing dramatic at the horizon. And third, that physics as known far from the black hole remains ordinary and consistent. They showed you could not have all three. If Hawking radiation really carries away every detail of what fell in, then the outgoing radiation far from the black hole ends up entangled in a way that conflicts with the smooth interior predicted by relativity. Something must give, and the AMPS team suggested the cost might be the calm horizon itself. Instead of a gentle crossing, the edge would become a searing wall of high-energy quanta, a firewall breaking the equivalence. Principle that says local physics should feel normal to a freely falling observer. It was a shocking claim because that principle is one of the most trusted pillars of Einstein's theory. The idea landed like a thunderclap. Some saw it as an unavoidable sign that our current understanding of quantum gravity is incomplete. Others viewed it as a signpost pointing the wrong way. Leonard Susskind would long champion the idea that black holes can act like holograms storing information on their surfaces, resisted giving up the smooth horizon, and argued that some deeper mechanism must resolve the paradox without firewalls. Juan Maldacena and colleagues explored connections between entanglement and wormholes. The ER equals EPR idea, hoping that if every pair of entangled particles is linked by a tiny non-traversable wormhole, then the interior and exterior could remain consistent, and no firewall would form. Hawking himself, though he had shifted his stance on information loss years earlier, did not embrace the firewall, but admitted the debate had reached new intensity. What made the discussion so fierce was that it was not about some exotic scenario far removed from testable physics. It grew straight out of trying to combine two otherwise solid frameworks, general relativity and quantum mechanics. Both have been verified countless times in their usual domains. But when we ask them to coexist at an event horizon, logical contradictions show up. The firewall was one blunt way to avoid the contradictions, but it felt like surrendering something precious, the smooth, graceful nature of space for a falling traveler. No experiment can settle the question yet. Event horizons are too distant and subtle for direct probes. Observations of gravitational waves from merging black holes, or of light skimming the edge, as with the Event Horizon Telescope, might one day reveal signs of new physics if firewalls or some other quantum structure leave imprints. But for now, the debate remains a thought experiment sharpened by mathematics. Entire workshops have been devoted to the black hole firewall paradox, with leading figures arguing late into the night about entanglement, complementarity, and the deep meaning of space and time. The implications go beyond black holes. If horizons are not smooth, if quantum gravity demands something violent there, then the idea that space looks locally flat to a falling observer might break down elsewhere under extreme conditions. It would also shift how we think about information and the flow of time. Some theorists have tried to salvage the calm horizon by proposing subtle, long-range connections between Hawking radiation and the black hole interior, but these suggestions are still being tested in models and toy universes simpler than our own, for non-physicists. The debate is both thrilling and unsettling. It shows that even now, after a century of general relativity and nearly as long of quantum theory, we have not completed the map. The place we thought most silent may hide violent new physics. The thing we assumed was an uneventful crossing could be, in some deep sense, possible. And yet there is also hope in the disagreement. Firewalls are a reminder that science is alive, that even widely accepted stories are not beyond question. They have pushed researchers to sharpen ideas about holography, quantum entanglement, and the emergence of space itself. They have forced the brightest minds to admit that we do not know what an observer truly meets at the edge of a black hole. Perhaps. One day a new theory will dissolve the paradox without firewalls, preserving the quiet horizon and saving the principle of equivalence. Perhaps not. Perhaps nature really does build invisible walls of energy when information tries to escape. Either way, the question of what lies at the boundary, smooth, dark, or blazing light, is now one of the central frontiers of modern physics. It is a strange place to stand, on the edge of seeing, where even the best mathematics collides with mystery, and where the answers matter not just for black holes, but for the very fabric of reality. Long before astronomers learned to weigh the dark hearts of galaxies, they imagined black holes as solitary and self-contained, lurking but otherwise irrelevant to the wider shape of the universe. Yet as better instruments mapped the skies and computer models grew more powerful, a very different story began to emerge, one in which the largest black holes are not just passive graves, but active forces that shape whole galaxies, sculpting stars, stirring and quenching gas, and guiding the fates of cosmic cities made of hundreds of billions of suns. These supermassive black holes, millions or even billions of times the mass of our sun, seem at first like quiet anchors. But their influence reaches far beyond their small central domain. The first clues came from the discovery that almost every large galaxy harbors one. In the 1990s, observations with the Hubble Space Telescope and with powerful ground-based spectrographs revealed that galactic cores often contain invisible masses with the right signature. Stars moving at dizzying speeds, gas swirling and heating under intense gravity, light broadened into wide spectral lines. When astronomers compared the masses of these central black holes to the surrounding stellar bulges, a striking pattern appeared. The heavier the bulge, the heavier the black hole. This relationship, called the M-sigma relation, because it ties black hole mass to the velocity dispersion of stars in the bulge, suggested some deep coevolution. Black holes and their galaxies seem to grow in lockstep, as though each knew about the other. Our own Milky Way is part of this story. At its center, far beyond the spiral arms and the quiet suburbs where our sun resides, lies Sagittarius A*, a black hole of about 4 million solar masses. Today, it is quiescent by cosmic standards. It sips only tiny amounts of gas and dust, glowing faintly in radio and X-rays. But evidence from surrounding structures hints that it has not always been so restrained. Vast lobes of high-energy particles called the Fermi bubbles rise tens of thousands of light-years above and below the galactic plane. Discovered by NASA's Fermi-Gamma Space Telescope in 2010, these ghostly shapes may be relics of an outburst a few million years ago. When Sagittarius A*, briefly fed with enough ferocity to light up the galaxy's core and blast material far into the halo. The Milky Way's calm monster, it seems, has the capacity for violence. Such feeding episodes can transform a galaxy. As gas falls toward the central black hole, it forms a hot accretion disk and can trigger jets or winds that drive energy outward. These outflows can heat or sweep away the cold gas needed to form new stars, effectively starving parts of the galaxy and halting star birth. In the largest galaxies, especially those at the centers of clusters, black hole feedback seems essential. Without it, models show they would form far more stars than we see. Astronomers studying clusters like Perseus or Virgo have found enormous cavities in the hot X-emitting gas. Carved out by past jet activity from central black holes, the jets inflate bubbles larger than entire galaxies, stirring and heating the cluster medium, cosmic thermostat, regulating growth. At the same time, black holes can also trigger creation. The pressure of outflows and shock waves can compress clouds of gas, provoking star formation along their edges. Observations of distant, bright quasars, the blazing beacons powered by fast-feeding, supermassive black holes, sometimes show surrounding rings of newborn stars, as if the violence at the center has sparked construction further out. Even in our Milky Way, some star-forming regions near the central molecular zone may have been nudged by ancient activity from Sagittarius. The dual role of destroyer and creator gives these black holes a strange personality. They are engines that can both quench and ignite, depending on how and where their energy flows. The same accretion disk that feeds them is also the source of the winds and jets that push matter away. The balance of these processes appears crucial to explaining the diversity of galaxies we see, some still making stars, others long dead and red, some small and disordered, others large and calm. Computer simulations like the Illustrious and Eagle projects have tried to capture this feedback in digital form. Seeding virtual universes with black holes and watching galaxies grow. When black hole physics is left out, the simulated galaxies become unrealistic, forming too many stars and failing to match the observed universe. Include the feeding and feedback, and suddenly the digital cosmos looks more like the one outside our telescopes. These experiments underscore that to understand galaxies, you must understand the monsters at their cores. For humans, there is something deeply humbling in this recognition. We orbit quietly around a star, far out on a spiral arm. And yet the shape of that arm, the rate at which stars like our sun were born, and the very chemical richness of our neighborhood are tied to ancient events around a dark object we cannot see with the naked eye. Long ago, Sagittarius A** likely flared and calmed, breathing energy into the Milky Way's heart, affecting how gas flowed and where new clusters took shape. The gold in our jewelry and the carbon in our cells were forged in stars whose formation may have been nudged, indirectly, by outbursts from that central beast. These insights also shift the emotional story of black holes. They cease to be only symbols of endings and erasure and become architects of form. Their destructive pull seeds order at larger scales. Their hunger restrains chaos. Even as they swallow, they organize and sculpt, turning random gas into coherent galactic structures. This vision is stranger and grander than the old idea of black holes as mere cosmic vacuum cleaners. It suggests a kind of reluctant partnership between creation and collapse, a dialogue that shapes the visible universe. In the Milky Way tonight, Sagittarius A** is quiet. Stars like S to continue their long, fast dances around it. Clouds drift inward but mostly survive. Life on Earth proceeds unaware of the dormant power at the center, yet the record of past outbursts hangs above us in gamma ray lobes. In subtle imprints on star motions, in the very pattern of our galaxy's growth, and in distant space, other black holes still roar, lighting quasars and blasting jets, enforcing the strange balance between building and breaking. To study them is to understand that darkness and light are not separate kingdoms, but intertwined forces shaping everything we see. When we look into the night sky, we are always looking backward in time. The stars appear as they were when their light began its journey, years or centuries or millions of years ago. With black holes, the past becomes even more elusive, because they do not shine on their own. Their presence must be traced indirectly, in echoes and distortions and ripples. Yet this very difficulty has given rise to a new field sometimes called cosmic archaeology, a patient search for the oldest and most hidden black holes, the ones that may have formed in the dawn after the Big Bang, and whose histories are written not in photographs but in faint light, radiation, and trembling spacetime. The goal is audacious, to use these dark objects as fossils, clues to how the universe built itself. One of the deepest mysteries is how the first black holes came to be so quickly. Observations of extremely distant quasars, whose light left them when the universe was less than 1 billion years old, shows supermassive black holes already weighing 1 billion suns or more. The question is how such monsters grew so large in so little time. Did they start as the collapsed cores of the very first stars, so-called population 3 stars, made of pristine hydrogen and helium, perhaps 100 or more solar masses each? If so, they would have had to feed at nearly the maximum rate allowed by physics, swallowing gas in torrents without blowing it away. Or did they form through direct collapse, where enormous clouds of primordial gas skipped the star stage entirely and fell straight into a black hole of tens of thousands of solar masses? There is evidence for both ideas, but no clear answer, and every new telescope aims to push further back to catch them in the act. Astronomers pursue this story with many tools. In light, they look for the faint glow of ancient quasars using wide surveys such as those done by the Sloan Digital Sky Survey and, more recently, by the James Webb Space Telescope, which can see the red-shifted signatures of early galaxies in their feeding cores. Webb's first deep fields have already uncovered galaxies so early and bright that they challenge growth models, hinting that black holes were helping shape the cosmic web from its infancy. Meanwhile, in X-rays, observatories like Chandra and XMM Newton search for the energetic signatures of smaller, but still voracious black holes at intermediate distances, hoping to fill the gap between early seeds and modern giants. But light alone cannot tell the whole story, especially because the first stars and black holes likely formed in thick clouds of gas and dust that absorbed much of their radiation. This is where gravitational waves promise a revolution. Each time 2 black holes merge, they send out a burst of waves that ripple through spacetime unimpeded by matter. The LIGO and Virgo detectors, and soon Kagra in Japan, have already caught dozens of such events. But these are mostly from relatively nearby stellar mass black holes. In the next decades, new instruments like the planned space-based LISA, the Laser Interferometer Space Antenna, aim to catch the lower frequency waves from supermassive black holes colliding across the observable universe. Those signals will be fossils of galaxy formation itself, direct messengers from a time before the first heavy elements, carrying pure gravitational memory of growth and merger. There are other relics as well, quieter but rich with history. The cosmic microwave background, the afterglow of the Big Bang first mapped by COBE and then WMAP and Planck, might carry subtle imprints of primordial black holes, if any formed in the first fractions of a second. Some theories propose that tiny black holes could have been seeded by density fluctuations in the infant universe. If they existed, they might still roam today as dark mass, or might have evaporated, leaving faint high-energy signals. Searching for these remains in the distribution of dark matter in unexplained gamma rays. In microlensing events, when invisible objects pass in front of stars, is part of this grand archaeology. What drives the effort is the sense that black holes, paradoxically, can preserve memory. While nothing escapes once it crosses the horizon, the very presence and mass of a black hole records how much fell in. And the gravitational waves of a merger encode the properties of the colliding pair. A single waveform carries the story of stars long gone, of gas that once swirled in forgotten galaxies. Light bent and delayed by intervening black holes tells us about the structure of space between here and there. Like tree rings marking time, this work is painstaking and slow. Teams compare models to observations, simulate countless mergers on supercomputers, and comb through faint signals hidden in noise. But each new detection adds a page to the cosmic ledger. The first LIGO event, GW150914, told of two heavy black holes formed perhaps from massive metal-poor stars. Subsequent events have hinted at strange mass ranges. Black holes too heavy for known stellar processes may be clues to exotic origins. Future space detectors will hear mergers from the very dawn, and radio surveys may find gravitational blending of early quasars revealing still more about how the first structures assembled. It is not lost on those who work in this field that they are, in a sense, historians with no archives but the universe itself. They cannot dig bones from the ground or brush dust from pottery. Instead, they dig in data, unearthing ancient cataclysms from signals that spent billions of years crossing silent space. There is a quiet romance to it. We build machines sensitive enough to hear a shudder in space-time smaller than a proton and send them hunting for events older than Earth. We turn light bent by invisible mass into a map of ancient darkness. Each discovery reminds us that nothing that happens is truly lost. It changes the cosmos in ways we can still trace if we learn how. This dream to read the universe's deepest memory is still young, but it is already reshaping our understanding of origins. Black holes, once feared as destroyers, are turning out to be record keepers and signposts, marking where matter collapsed, where galaxies formed, where time ran differently. They show that even in the farthest past, in ages before stars like our sun, there were forces fierce and organized enough to leave legible marks. And as new observatories join the search, we are coming closer to reading the first pages of the cosmic story, written not in ink or stone, but in gravity and the faintest glow of ancient light, in the great silence that surrounds black holes. It can feel as if they are forever beyond the reach of experiment, too distant and too strange for hands and instruments built on Earth. Yet one of the most striking qualities of modern physics is its refusal to be stopped by distance. Scientists know they cannot bring a black hole into a laboratory or send a probe across its horizon. But that does not mean they give up. Instead, they build machines and models that recreate pieces of black hole behavior. And they run vast simulations inside supercomputers that let them watch collapse and feeding in jets without leaving the planet. Bit by bit, they create an experimental bridge to phenomena that would otherwise be only math and imagination. One of the most famous arenas for this work is the world of particle colliders. Facilities like the Large Hadron Collider near Geneva are not built to make full black holes. The energies are far too low for that. But they can explore physics close to the conditions expected near a horizon. When protons collide at nearly the speed of light, the energy density for an instant becomes enormous, bending quantum fields in space-time in subtle ways. Some speculative theories of extra dimensions once suggested that microscopic black holes might briefly form in such collisions, evaporating almost instantly with a spray of particles. Although none have been seen, the very search puts limits on those models and teaches us about gravity's behavior at small scales. The detectors at the LHC, built with exquisite precision to measure the debris of collisions, are in a sense microscopes for space-time itself. Beyond smashing particles, physicists also build analog black holes, tabletop systems where the equations match those of horizons, even if the materials are ordinary. One famous approach uses fluids or Bose-Einstein condensates cooled near absolute zero. In these setups, sound waves or light pulses can be trapped in ways mathematically identical to how gravity traps photons. In 2010, a team in Israel led by Jeff Steinhauer reported creating an acoustic black hole and detecting a faint signal analogous to Hawking radiation. Ripples in the quantum field of sound. The results are debated and refined. But such experiments show that key pieces of black hole physics can be tested with clever substitutes. Other groups have made optical horizons in fiber optics where pulses of light slow down and trap other photons, again mimicking the edge where escape fails. Supercomputers extend this ingenuity on a cosmic scale. The equations of general relativity are famously hard to solve in anything but perfect symmetry. But numerical relativity, feeding those equations into massive computer clusters, lets scientists watch black holes merge, twist space-time, and generate gravitational waves. These codes were critical long before LIGO's first detection. Without them, there would have been no templates to match the faint signals. The simulations show not only how waves rise and fade, but also how matter behaves near horizons, how jets might form, and how magnetic fields evolve in disks. They are laboratories made of mathematics and silicon, turning raw theory into movies of collapse and collision. Sometimes the experiments are about clever observation rather than direct creation. Instruments like the Event Horizon Telescope are not just cameras, but enormous coordinated experiments in signal processing and data combination. Gravitational wave observatories themselves are feats of experimental courage, giant interferometers pushed to the quantum limits of measurement. So sensitive, they can feel the passing of waves that stretch space by less than the width of an atomic nucleus. To suppress noise, engineers suspend mirrors on glass fibers, cool and isolate them, and use squeezed light, a quantum trick to push precision beyond classical limits. Each detection of a merger is both astronomy and experiment, a confirmation that our tools can touch reality at a scale once thought unreachable. These efforts have a particular spirit, a refusal to accept that some questions are forever out of reach. When faced with the cosmic limits imposed by distance and invisibility, scientists look for ways to recreate conditions, to coax analogies from nature, and to combine signals from across the globe until the planet itself becomes an instrument. They know that every test has boundaries. A fluid horizon is not the same as a gravitational one, and sound quanta are not photons, but each partial success narrows the unknown and builds confidence that theory and reality still walk together. The work also shapes how we teach and imagine black holes. Without numerical relativity, the famous visualization in the film Interstellar, with its warped accretion disk and double-lensed light, would not have been possible. Without tabletop horizons, Hawking radiation might remain forever, a line of algebra instead of a thing students can try to glimpse in a lab. These connections pull the distant into reach, making black holes less like distant myths and more like physical entities we can probe from here. At the edge of what is knowable, there's also a sense of humility. Every experiment is a translation. The real horizon remains beyond our touch, yet progress comes anyway. Each new detection of gravitational waves forces better models. Each analog experiment tests pieces of quantum field theory in curved space-time. Each collider result constrains exotic physics that might lurk near a singularity. Piece by piece, a structure grows where once there was only darkness. For humanity, this ingenuity is more than technical. It is an answer to the void. We are creatures who cannot go where we long to go, so we build windows. We cannot visit a black hole, but we can make one whisper in the language of fluid waves or let two protons collide so hard that space itself trembles. We cannot survive beyond an event horizon, but we can build instruments sensitive enough to hear the moment others merge. In doing so, we take something unreachable and bring it within the scope of reason. There is poetry in these efforts. We live on a small planet circling a modest star. Yet we can replay on our screens the merging of titanic black holes, billions of light years away, and watch fluid ripples stand in for horizons that would tear us apart. To experiment at the edge is to refuse despair before the universe's vastness. It is to believe that curiosity, coupled with patient craft, can turn even the most remote and dangerous phenomena into something that yields a little truth. The black holes remain far and silent. But here on Earth we have learned to make them speak. The idea that the universe might have a memory is not new, but nowhere does it feel more haunting than when we think about black holes. For centuries, humans have buried their dead and left marks on stone or paper because we fear forgetting. We have built libraries, photographs, and digital archives in the hope that nothing essential will vanish. Yet the cosmos seems vast and indifferent. Stars are born, burn for eons, and die. Planets melt or freeze or are flung into darkness. Light itself thins and fades. When black holes entered science's vocabulary, they seemed to sharpen that fear. Here at last was a place where not even light survives, a vault so perfect it might as well be oblivion. But as our understanding deepened, an odd shift occurred. Black holes began to look less like erasers and more like strange keepers of record. Holding on to some kind of ledger even as they hide everything from view, it starts with the simple fact that a black hole remembers. The things that fell in, at least in a coarse way. Its mass, spin, and electric charge tell you something about its past. If a star collapses, or a whole cluster of stars merges and feeds a central giant, the black hole grows heavier and its rotation changes. Even if the details of each particle vanish, the total remains. John Wheeler used to say that black holes have no hair, meaning they look simple from the outside. But even this minimal simplicity is a kind of story, a record of how much was devoured and how the devouring happened. The gravitational field itself is a memory, shaping the orbits of nearby stars and bending the paths of light for millions of years. We also know that black holes mark events in a language we can hear. Every time two of them merge, they release gravitational waves, and those waves are literal history passing by. When LIGO detected its first signal in 2015, the chirp of two black holes, 1.3 billion light years away, it was catching the last heartbeat of a system long gone. The waves were faint, but exact, by decoding their pattern. Scientists could tell the masses and spins of the vanished pair, like listening to a bell and knowing its shape. Each detection since then is a memory released, a way for the universe to announce, these giants lived and collided. Their moment is not lost. In that sense, every black hole merger adds to a cosmic archive written not in light or stone, but in the geometry of space-time itself. There is another, more subtle kind of keeping. When matter spirals toward a black hole, it heats and shines before crossing the horizon. That light can travel forever. We see quasars from the early universe, some shining when Earth was only dust and gas powered by feeding black holes. The details of the swallowed galaxies may be gone, but the last radiation they gave off on their way in is still arriving. Even our own actions echo faintly. The radio waves we have been leaking for a century race outward, one day, unimaginably far in the future. Some may brush the event horizon of Sagittarius A** and vanish, but until then, they are part of the long record. Nothing that radiates dies quickly in a universe so big and so empty, and yet there is real loss. The information paradox, the question of whether the fine details of what falls in are forever erased, remains a wound in physics. Stephen Hawking's work implied that as a black hole slowly evaporates through Hawking radiation, the outgoing particles know almost nothing of what went in. That would mean true forgetting, a breaking of quantum law. Many now suspect the story is subtler. Somehow the quantum details are encoded in the horizon and leak out over the black hole's long life. No one can yet show exactly how. So for now, the fate of perfect memory is uncertain. The universe might, at its deepest level, preserve every pattern, or it might let some stories go quiet forever. For those of us watching from this small planet, that tension becomes strangely emotional. To know that black holes store at least the great measures of what they consume, weight, spin, momentum, and that their mergers ring out like gongs across billions of light years, is comforting. Something of every star and planet survives as a mark on space-time. But to suspect that the finer details, the exact arrangements of atoms, the complexity of life and thought, may vanish when swallowed is sobering. The cosmos might keep the headlines, but not the pages. And yet even those headlines are precious. They allow us to practice a kind of cosmic remembrance. We turn telescopes toward the center of our galaxy and watch stars like S to whip around an invisible mass. Proof of Sagittarius A* and everything it has eaten. We build interferometers so delicate they can feel the echo of ancient collisions. We gather those echoes and build family trees of black holes, tracing how the universe built structure and complexity. In doing so, we act almost like archaeologists of the infinite, piecing together lives and deaths from the faintest residue. There is also a deep poetry in how these records reach us. The light from a feeding quasar, left when there were no humans and perhaps no solid Earth. The gravitational wave from GW 150914 began traveling when multicellular life was still simple on our planet. To detect it is to receive a message from deep time, proof that what happens is not fully gone. Even the darkest objects cannot quite erase their footprints. So the memory of the universe is complicated and bittersweet. It is not the gentle archive we might wish for. It does not keep diaries of civilizations or photographs of faces. But it is also not empty. Mass and motion are tallied. Collisions echo. The shape of space bears scars of every fall. And as our instruments grow better, we learn to read those scars. We, fragile and brief, have built ways to listen to black holes, and in that listening, discovered that the cosmos forgets more slowly than we feared. It is not the kind of memory that can tell us who we were, but it is a promise that nothing, not even the end of light, is completely silent. From the beginning of this long journey, the question has stayed the same and yet grown deeper with every step. When a black hole swallows stars and planets and light itself, where does it all go? We have followed Einstein's hesitant predictions and Carl Schwarzschild's lonely calculations from the trenches of 1916, traced the life and death of giant stars collapsing under their own weight. Watched radio astronomers in the 1960s stumble onto signals that forced theory to face reality, and stood with scientists in 2019 as they unveiled the first direct image of a black hole's shadow. We have learned how space can ripple like water when black holes collide, how Hawking's insight that they radiate redefined what forever means, and how whole galaxies dance to the tune of these dark hearts, and still the final secret is intact. After a century of progress, the place beyond the horizon remains closed. The attempt to reach that place is more than curiosity. It is part of what it means to be human. We have always tried to go where we cannot. When sailors lacked maps, they made them. When the far side of the moon was just a blank, we sent spacecraft. Black holes tempt us in the same way. But here, the challenge is more profound, because physics itself seems to warn that no path returns. Yet we keep building thought experiments and instruments as if knocking on a locked door might someday cause it to open a crack. LIGO and Virgo hear the last cries of merging holes. The Event Horizon Telescope stitches together a planet's worth of data to look directly at their edges. Particle colliders crash protons to glimpse the physics of horizons. Tabletop analogs of black holes hum quietly in labs. Each effort is a hand against the door at the same time. We have begun to accept that some mystery is not failure, but part of the beauty. The very reason black holes are compelling is that they draw a boundary between what we can measure and what lies beyond. They remind us that nature can be known in parts, but not in total, at least not yet. Even so, the pursuit itself reshapes us. Trying to understand how information behaves at a horizon has led to new ideas. About quantum entanglement and space-time itself, wrestling with the paradox of memory has forced us to reimagine what a place means when space and time become fluid. Even if the door never opens, the path toward it changes the map of everything else. There is comfort in that view. The universe does not yield its deepest truths easily, but it rewards honest work with glimpses, the faint tremor of a gravitational wave, the orange ring of M87*, the quiet jets from feeding monsters that sculpt whole galaxies. Each discovery is like light leaking through a keyhole. They do not tell us what is inside, but they tell us the door is real, that our questions are not wasted, and there is poetry too, perhaps more than anywhere else in science. A black hole is ultimate loss and ultimate survival at once. It is the end of stars, but also the keeper of their mass and the sender of their last message in waves and light. It is a place where clocks end, but story somehow continues, written in the fabric of space, even if the details fade. When we ask where everything goes, we are also asking what remains of us, our planets, our signals, the brief radio murmur of our species. We may not like the answer, but we cannot stop seeking it, so we keep watch. We tune our detectors to the faintest tremble. We trace the paths of stars around Sagittarius A*, as Andrea Ghez and Reinhard Genzel have done, hoping every orbit tells a little more about the core. We feed supercomputers with equations that run for months just to simulate a few seconds of cosmic collapse. We imagine what an astronaut would feel in the silent plunge past the horizon. None of this brings us closer to crossing the line, but all of it makes the darkness less blank. Some nights the Milky Way stretches overhead, and you can imagine the center where our own black hole waits. It is quiet now, but not dead. It has fed and will feed again. Around it, swirl records older than humankind. We stand impossibly far, yet still able to sense its pull and even map its shadow. That alone is astonishing. A small primate species on a small planet has reached with mathematics and machines across 26,000 light years to outline something from which no light returns at the end of all the chapters and all the questions. Maybe what matters is not the final answer, but the act of asking. To live in a universe that can swallow light and still let us wonder about where it went is to live in a place that invites exploration even while setting limits. We may never bring back a piece of what has fallen in. We may never decode the complete memory. But we have learned to hear the echoes and to read the scars. And that is its own form of knowing, so the door stays closed. Black and silent, yet surrounded by a glow of understanding we did not have before. Our instruments stare across unimaginable gulfs. Our theories reach into paradox and return with fragments of insight. We are not finished, and may never be. But perhaps that is the correct ending, not a solved puzzle, but a quiet, enduring question. In the mind's eye, the final image is simple. Deep space. A dark sphere burning faintly at its edges with light twisted by gravity, the last signal of everything that dared to approach. And somewhere, far away on a tiny world, we keep watching, keep listening, and keep knocking.